So chapter 15 is pretty much a continuation of chapter 14. We're still looking at acids and bases. We're still looking at equilibrium systems. Now, though, we're going to add something called a common ion. Now, let's assume we have a weak acid. My weak acid does not dissociate completely, so the reaction goes both ways. Now, if I have my weak acid equilibrium and I add a salt, here my acid is HA, where A is just the generic ion. If I've got NaA added to it, then this A minus is called a common ion because it's both in the acid and it's in the salt. Okay? Now what this will do is it will have something called the common ion effect. Now what this will do is it will shift the equilibrium. Because my equilibrium already has the ion in the equation. So here's what it looks like. Here I've got an HF equilibrium. So I know that hydrofluoric acid is a weak acid. It does not dissociate completely, so the reaction goes both ways. When it breaks apart, it'll break into H plus and F minus. If I add a solution of NaF, in solution, NaF breaks into Na plus and F minus. This F minus is the same as this F minus. Because I'm adding product, I shift the equilibrium to the left. So if I add my common ion, I'm going to shift the equilibrium position to the left. Take a second to solve example 2. If I add NH4Cl to a solution of NH3, what will that do to the equilibrium? Write your equation for NH3 and determine, will it shift it to the left, to the right, or will it have no effect? Now, because adding a common ion shifts the equilibrium, it'll also change the concentrations. So here I'm actually asked to calculate the concentration of H plus in the HF solution. They give me my Ka for HF, and they tell me that I'm adding 1 molar NaF. So here's the way that this works. It's a little different than what we did before. I still have my equation. Hydrofluoric acid is breaking into H plus and F minus. I know that I have 1.0 molar HF initially. I know that initially none of this is broken apart, so I have 0 H, but this is where it gets different. My solution also has 1.0 molar NaF, which is broken apart, so initially I also have 1.0 molar F minus. So now I want to figure out my H plus concentration. I know that this is going to break apart, so it's going to go down. I know that it's going to form my products, so this is going to go up. Just like last chapter, I'm going to assume that the amount of this that goes up and the amount of, goes down, and the amount of this that goes up is going to be so small to the initial concentration that for math simplicity's sake, I can ignore that. So here's what it's going to look like. I know that my Ka is equal to the concentration of my products divided by the concentration of my reactants. I know that HF starts out as 1.0 molar minus X. I ignore that, so it stays H plus. Let's strike that. H plus, I don't know. H plus is going to be X. F minus, I do know. F minus is the 1.0 times 10 to the negative X, or sorry, 1.0 plus X. I'm going to ignore X, so that's the 1.0. And then, as I was saying before, my HF is 1.0 minus X. I ignore that minus X because it's not a big change. So these two things are going to cancel out. I'm told that X is equal to 7.2 times 10 to the negative fourth. X is going to be equal to my H plus concentration. So at equilibrium in the solution, H plus is equal to 7.2 times 10 to the negative fourth molar. Okay? Now a buffer is a very special type of equilibrium system, a very special type of the common ion effect. Now what a buffer does is it's a solution that is going to resist a change in the pH. So it resists it if I add either H3O plus, hydronium ion, my acid, or if I add OH minus hydroxide, my base. A great example of a buffer is our blood. Our blood can't change pH drastically. If it did, then we'd die. That would be a bad thing. Now remember we said last chapter that CO2, when it dissolves in water, is actually going to form carbonic acid. Now when we breathe in oxygen. Our body converts that into carbon dioxide, which my blood is going to carry to the lungs so that I can exhale it. Now, since I've got that carbon dioxide in my blood, it converts to carbonic acid. That's what happens when you work out and you get that buildup of acid in your muscles. Now, if my body wasn't able to counteract that pH change, my blood would become extremely acidic and I'd die. But because my blood is a buffer, it resists a change in the pH. Now the way that a buffer works is it's going to have either a weak acid and its salt. Now oftentimes you'll hear me call this the conjugate base. So an example is one we talked about before. I can have HF, which is my weak acid, and if I add NaF, that's its salt, the F minus is the conjugate base. Or a buffer can contain a weak base and its salt. Again, you'll often hear me call this the conjugate acid. So the example we talked about before was ammonia with ammonium chloride. Ammonia is a weak base. The NH4 is going to be its conjugate acid. Now I have to have both parts. I have to have a common ion, okay? So when I have a buffer, it works exactly like the problem I just solved, okay? So I've got acetic acid. It's a weak acid. In water, it's going to break up into H plus, C2H3O2 minus, and the acetate ion. I initially have 0.50 molar acetic acid. I don't know how much H plus I have, and I'm adding 0.50 molar sodium acetate. So take a second and calculate the pH of my solution. Remember, once you solve for your H+, like we just did in the previous problem, pH equals the negative log of H+. So we said that a buffer is designed to counteract changes in pH. So let's take a look at that. So we're going to look at the same buffer that we just solved the pH for. So this is HC2H3O2, acetic acid. I've got H+, and I've got acetate ion. Sorry, that's an H. Okay. Again, it's the same example above. So initially I had 50 of this. I had 0.50 of this. I didn't know how much that was. But now I'm going to add a base to my system. Now this is going to change my concentration. So I'm adding 0.010 molar base. My base is going to neutralize my acid, so I'm going to subtract this. So I get 0.49. If it neutralizes my acid, it's going to form more of the conjugate base. So I get 0.51. And then it's exactly like the problem before. So I'm going to solve for H+. They told me my Ka is 1.8 times 10 to the negative fifth. This time I have 0.51 times x divided by 0.49. If I solve for x, I get that x is 1.73 times 10 to the negative fifth. That's my H+ concentration. So if I wanted to solve for the pH, pH is the negative log of 1.73 times 10 to the negative fifth. So I get that my pH is 4.76. In the last problem, we calculated pH of our initial buffer system. You should have had that was equal to 4.74. If we compare a pH of 4.74 to a pH of 4.76, we can see that adding just a little bit of base had very little effect on my pH overall. So remember, buffers are designed to contain a weak acid or a weak base and its common ion. When we have a buffer, if we add a strong acid or a strong base, we need to take into account how it changes the initial concentrations. That's what we did here. And it only works because the concentration of my initial weak acid or weak base and its common ion are going to be very large compared to the amount of acid I'm adding or the amount of base I'm adding. Okay?